With chapter 7, we begin several chapters of a building motion. So what we learn about confidence intervals in chapter 7 is going to be built on when we move into one population hypothesis test in chapter 8, which will then be built upon by two population hypothesis tests in chapter 9. So we have building blocks, and you need to really understand this first chapter 7 in order to be able to do well in the upcoming chapters. On your calculator, okay, there are a lot of different choices of items in the test menu after you hit the stat button. To simplify things for you quite a bit, I've got this diagram here showing you which items we will never be using. In chapter 7, we are going to be focusing on intervals, and specifically the T interval, which is option 8, and the 1 proportion Z interval, which is option A. Then we will move on in chapter 8 to move on to the T test and the 1 proportion Z test, both dealing with a single population. And then in chapter 9, we'll start to use some of the others. Okay, so right now in this chapter, we're going to be focusing on just these two, and we begin with the T interval and then move into the 1 proportion Z interval. We will be using T curves anytime we are dealing with means, and we will be using Z curves and inverse norm anytime we are dealing with proportions. Okay. There are other textbooks and authors out there that use the Z test instead of the T test. And as we move forward, I will explain to you why we at VBC are only using the T test. Okay, so in section 7.1, we introduce T curves to you. Basically, when you look at these pictures here, they're basically just like the normal curve with an exception. Okay, each T curve is tailor-made to go along with a particular sample size. In this picture, the black curve at the top center is your standard normal Z curve that you are used to, but we've got a couple of other blue curves drawn in. This DF stands for degrees of freedom, and it's always one less than the sample size. So when I have degrees of freedom equals 6, that basically means the sample size was 7. And when you have the degrees of freedom equals 1, the sample size was actually 2, because the degrees of freedom is 1 less than the sample size. Now, starting at this navy blue curve, which has degrees of freedom 1, as you increase the sample size, this curve is going to get taller and taller in the center, and you can see that it's going to flatten out and widen at the bottom also. But as the sample size increases, the dark blue starts to morph into this light blue, which will then later morph into this black curve as the sample size gets large enough. Okay, now we have some properties of the T curve, and one of the key ones is that we must assume the sample is taken from a population that is normally distributed. Now, that's an important thing that we're going to be looking at, and we will be talking about this major assumption throughout this course here, the rest of the course, and we are going to hope that the problems that we have tell us that the data is normally distributed. If it isn't normally distributed, then we need to check for normality. We've got to be careful in the language that we use here. Now, properties of the curve, these are all pretty much just like what you have for the standard normal curve. All the area under the T curve is equal to 1, just like what we have for the Z curve, so that we can do probabilities with it. And probabilities are percentages adding up to 100%. A T curve extends infinitely along the x-axis, left and right. It's symmetric around 0. And here's that new one that I was talking about. As the number of degrees of freedom increase, the T curve looks increasingly like the standard normal curve. Now we've got a little notation, we're not going to use very much here, but T subscript alpha, if I wanted to identify, for example, a shaded region right here where I said I'm going to shade in alpha, a certain area, the T value that has alpha to its right would be T subscript alpha. Now, if we were on the left side of center and we had alpha to the left, that T value which has alpha to its left would be negative T subscript alpha. Now, we are used to looking at z of alpha over 2, and we'll get a little bit more into that, and it's the same exact concept. This will not be a calculation you'll need to do in our course because the calculator will do it for you, but I wanted to let you know that that is available to you. And just as we go under the inverse norm curve on our calculator, let me show you how you can go. Let me go back to our main screen here. Let me not do that. Let me hit distributions, second distributions. You are used to inverse norm, choice 3. Now we've got inverse T, choice 4 available to you. So I thought I'd just call that to your attention, even though we will not be using the inverse T in this class. Okay, continuing on here, I've already just mentioned this inverse T to you, and I show you how to use it here. We won't be doing that. I want to move on to this idea of assessing normality. We hope that the word problems tell us that the data is approximately normally distributed. If they don't tell us, we need a procedure. So the main procedure we're going to use is that of a probability plot. Okay, in this section, we plot the data versus what we call normal scores based on the sample size. The idea is that we wish to know if the data is approximately normally distributed. So these are our two criterion in these two bullets. If the graph that we get, this normality plot, is roughly linear, then we accept as reasonable that the population is approximately normally distributed. If the graph has curves, then we conclude that the population is not approximately normally distributed. So I have a data set here in this first example, and I'm showing you the normal probability plot that goes along with it. And we look at whether it's roughly a straight line or whether it's curved. And you can see in this problem that it's rather curved. So when we assess the normality, we're going to say, since this graph is not linear, we can assume that the adjusted gross income, that's what the variable was there, for income levels, are not approximately normally distributed. So we basically went along with the second bullet that you see in that list there. Now, how do you create this normal probability plot? Okay, well, I have a couple more of these before I show you. I have the same data set almost. The one at the left has an extra point on it that is definitely an outlier. Okay, it's actually a potential influential observation point, but we'll talk about that later. And you notice how that messes up the straight line that we see, that we would see going through the data. Now, we're never going to have a perfectly straight line, and we are going to be a little bit generous when the sample size are smaller to a little bit of deviation from a straight line. But when we look at this problem, there's two possible conclusions we can make. Okay, first off, I wanted to show you the effect that an outlier can have on this normal probability plot. But this one is dealing with chicken consumption. I took it out of some picture I found somewhere online. Since the normal probability plot is approximately linear, we can assume that the distribution of chicken consumption is approximately normal. That would be based upon this first picture. But since this next one has an outlier that doesn't fit within that line, that would be where we'd say, since the normal probability plot is not linear, and probably even say and it appears to have an outlier, then we cannot assume that the distribution of chicken consumption is approximately normal. So basically, you're going to just describe using these two sentences, and I've got chicken consumption underlined because that's the variable here. For any particular problem, you'll just change out what that variable is, and you've got your sentence describing why or why not a data set is approximately normally distributed. Now, what if you don't have the raw data to use to construct such a normal probability plot? Well, then you can go and look at a box plot, box and whisker diagram of the same data. Now, if that is the case, you're basically checking the box plot for symmetry and the presence of outliers. We can see there's no outliers here, and it's pretty darn symmetric. Okay, each of these segments is about the same length. I wish that right tail was a little bit shorter, and maybe that center line representing the median was a smidgen to the left. But for all intents and purposes, this would be something telling us that, yes, I think the data is approximately normally distributed. Okay, now on to our calculator. I've got this word problem here, which we don't really need to look at. We just need to construct a normal probability plot for the data and analyze the results. You are going to go into your stat plot area. Now, to remind you, going back to our calculator, you're going to hit second stat plot. And then when you go into your stat plot area, make sure it's turned on. I have it set up for linear regression right here, but you would move that all the way to the far right option there, choose it, and that would be your normal probability plot, and then you tell it what list contains your data. So that's basically how you will do this on your calculator. So I've done this already for this data set. I've actually generated both the normal probability plot as well as the box plot for that data set. And we don't see any outliers in this data set, and this is roughly a straight line. So in this case, I would say, since the normal probability plot is roughly linear, we can assume that weekly food costs are normally distributed. And weekly food costs is what this variable is about if you go back and read the problem. Okay, so this is just something we're going to do on rare occasions when the problem does not tell us whether or not the data is approximately normally distributed. We hope to see those words within each problem, but we do have a method here for testing that. And why do we need to know about the normal distribution? Well, that is a necessity in order to use the t-intervals and the t-tests that we're going to be using in this second half of the class. Now let's change our method of what we're looking around, and let's start talking about what is a confidence interval. And we're going to start by talking about a point estimate. A point estimate for a parameter. Okay, let's go back and talk about what a parameter is. We know how we have X bar is a sample statistic used to predict the parameter mu. We know how S is a sample standard deviation to predict the population standard deviation sigma. And we also are going to be learning about proportions, where we have a sample proportion, p hat, which we use to make a prediction about a population proportion p. And so we're always using statistics to make a prediction for what that population parameter value is going to be. Well, these point estimates are these values that are on that top row there. Okay, so for example, we want to know what the mean purchase price of Victor Valley homes might be. So we might take a sample of about 500 homes and we compute X bar, the sample mean. This would be a point estimate for mu, a prediction, so to speak, for mu is the actual mean value. We took a large sample of 500 homes, and we know that the larger the sample, the more accurate our prediction is going to be. Now, anytime we make a prediction, hey, the mean price is such and such, we don't know if it's going to be right there on the nose. So we create a confidence interval around it saying from here to here. But not only just, hey, I think the interval's from here to here, we attach a level of confidence. Okay, so here we go. A confidence interval estimate of a parameter consists of an interval of numbers obtained from the point estimate. We start with that point estimate together with a percentage that specifies how confident we are that the parameter lies in that interval. Now, we're going to talk more about the meaning of this level of confidence at the very end of this chapter. But for right now, it's just kind of how confident or how sure are we? The true meaning is in this next paragraph, which is really going to be talked about at the end of the chapter. Okay, the confidence percentage is called the confidence level. And if we were to draw many samples, many different samples of size 500 of houses, okay, and then use each one to construct a confidence interval, then in the long run, the percentage of confidence intervals that cover the true value would be equal to the confidence level. Okay, it's kind of the in the long run way of looking at things, just like we talked about in the long run when we dealt with the expected value a couple chapters back. Okay, how do you go about doing a t-interval? Well, you go into your stat menu. Choice 8 will be our t-interval when we get there. And once you get to there, you have two choices of menus. Okay, you have the word data, which is blacked out here, or stats as our two different choices there. And you use data when you actually have a list. Notice how I've got list 1 right there. But if you don't have the data in the list and you just have the summary statistics, then it asks you what's the mean, what's the standard deviation, and what is your sample size. See, if you've got your data in a list, it already knows the mean, the sample standard deviation, and the sample size already. Okay, and then both times you're going to say, hey, here's the confidence level that I want to have, in this case 95%, and then we'd hit calculate, and out comes the interval that we are interested in. Okay, so if you could please pause this video and type in these 30 numbers, we will be using these actually for quite a while, so it's worth having these typed in. I'm going to let you pause this and then we'll join it again. Okay, let's read this problem now. An educational psychologist at a large university wants to estimate the mean IQ of the students in attendance. So he or she samples a random sample of 30 students, and there's the data that you've typed in on what their IQs are. So use the data to obtain a point estimate for mu, the true mean of all students attending the university. Now, we don't know the true mean. Okay, we'd have to IQ test every single student at the university, and that would be rather hard to obtain. So that's why we use our sample to make that prediction. And our sample mean, when you go into the one variable statistics, ends up being 109.8. Let me just review with you how we get there. So I'm going to go back to my calculator here. I'm going to quit out of this screen. I've already typed in that data into list 1, and you should know you hit your stat button, you go over to calc, hit one variable statistics there, and tell it your data is in list 1 and hit calculate. And there we have our mean of 109.8, and we have our sample standard deviation and population standard deviation there with all the different summary statistics that we are used to. So that was our sample mean that came out of the data. Now, part B asks, is it likely that our estimate is exactly equal to the true mean mu? And my answer is going to be no. Why not? Well, there's sampling variation. We took a sample. We didn't take a census, and so there's going to be some variation, but we understand that. So now we move on to finding a confidence interval. Now, the first one we're going to do manually. You can see in part D, we're going to use our calculator, but we're going to start manually here. And I'm going to say find a 95.44% confidence interval for the mean IQ of all students attending this university. Now, why 95.44%? Well, hopefully that number sounds familiar to you, because that goes along with 2 standard deviations from our 68, 95, 99.7 empirical rule. So that's why I'm starting there. Now, we never want to use a 95.44% confidence interval. Usually we want a nice clean number like 95%, 90%, 99%, 98%, but not anything with this decimal here. That's just a little bit strange, and we just wouldn't talk that way. So let's do this manually. Well, we're going to start with our mean, and I probably, instead of mu, should have listed X bar there, because there's my X bar, 109.8, plus or minus. Now Z is 2. Okay, that's what we chose to do with the 95.4. Then I'm going to plug in here the sample standard deviation and our square root of 30, which was our sample size that we have over at the left. And I've got a comment here that we could calculate this sample standard deviation S by going into that one of our stats menu, which I showed you a moment ago. And when you actually crank this out, you have plus or minus. You're going to find this value on the right, and you're going to both add it and subtract it. So that value on the right ends up being 4.0371. And when you add and subtract it from the 109.8, you get an interval which goes from 105.7629 up to 113.8371. We would be 95.44% confident that the true mean IQ of all students attending the university is inside that interval. Now I say, let's do this using our calculator. Now, because you've got these numbers typed into a list, okay, this is actually 2 screenshots here. This is what you'd see on the T interval screen when you go to type it in. We choose the data option. We tell our data is in list 1, and we then tell the calculator we want to do a 95% confidence interval. When we actually do that, and it's 95, not 95.44, out comes the T interval that we want. And as an extra bonus, it tells us what the mean, the sample standard deviation, and N were. We didn't really actually calculate them if we just type these numbers into the screen. So it gives it back to us as a bonus, but we only need that top line there. And I've got another comment here that says we will always use numbers like 95, 99, nice clean numbers. Now, what does this confidence interval mean? I'm asking us to interpret this in 2 ways. Okay, well, here we go. First one is 95% of the students have IQs between these 2 numbers. Okay, that's a general statement. But then I have a more specific statement that says there's a 95% chance that a randomly selected student has an IQ between these 2 numbers. And that gets specific to a single student. It depends on if we're going general, if we're going specific. So I just wanted to give you those 2 different explanations of what this interval means. Now keep these numbers in your calculator, because we're going to be still using them as we move on. Okay, now we're going to move on and talk about the margin of error and sample size. Now, we've talked about this plus or minus, and anytime you have an interval, it's centered around your, in this case, mean, and we're going plus or minus. Okay, so here's our plus and here's our minus going to the left, some margin of error, which is known as the maximum error of the estimate. And it's got this formula here on how you can calculate it. And by the way, anytime you see Z subscript alpha over 2, that basically is inverse norm under the standard normal curve of alpha over 2. And we'll use that notation instead, but I wanted to let you know that. But notice how when you go plus or minus, it's not just the standard deviation that's involved. There's basically 3 ingredients that make up this margin of error. One of which is that standard deviation. But if you remember back to when we learned the standard deviation, we know that the standard deviation doesn't talk about the direction of the deviation. That's why we need a plus or minus involved. But we also need this square root of n, because how large a sample we take is going to play into the level of accuracy. And in the central limit theorem in the last chapter, we learned about sigma divided by root n being the maximum error of the estimate, yeah, I guess I should call it that. And then we have this z of alpha over 2, where this is related to our confidence. Okay, now let's go to this picture right here. Confidence and significance are words that are complements of each other. They always add up to 100%. So when there's a 90% confidence level, we say that there is a 10% significance level. If we've got 95% confidence, then we've got 5% significance. In both of those cases, they add up to 100%. Now, let's go with this 95%. If I were to draw a picture here and say, ooh, 95% fall within those regions right there, we're saying we're 95% confident of that. But isn't there 5% left over here where I say, between that tail and that tail on the right, there's still 5% left over. And due to symmetry, we cut that 5% in half. So we say in this problem, alpha would be 5%. Half of that alpha would be 2.5%, 0.025. And so we would have the z value over here at the right that has alpha over 2, or the 2.5% to its right. And over here on the left, we'd have negative z of alpha over 2, having the 2.5% to its left. Now, when you want to find the margin of error, you can use this formula here, but there's an easier way. That E is half of the length of the confidence interval. Okay, thinking of it as the plus or minus. So if you know how wide that interval is, you can just divide that interval's width by 2, and you've got one error going down and one error going up from the center. You'll see this in action in just a moment. Actually, let me go forward a couple of screens. Let me show you this right here. Here is a pretend interval I have for you. I just made it up because the numbers are clean. If I were to ask you, how wide is that interval? You go, oh, from 40 to 100, that's 60 units wide. You can find that by subtracting. If I said, what is the point estimate? What's the number that's right in the middle of that interval? You might just be able to eyeball it and say 70. But there is another way to calculate that 70, and that would be just by guessing, as we said, or you can add up and divide by 2. Find the mean number of that interval, 40 plus 100 divided by 2, and there's your 70. So 70 is in the middle, and if I were to draw a picture of this, I'd have this number line, 70 is in the middle, and I'd be going up 30 to get to this 100, and I'd be going down 30 to get down to 40. So what is the maximum error of the estimate? Well, you already know it's 30 there. We've added and subtracted 30. How can you do that more easily? If you know how wide the interval is, you just cut that in half, and there's your 30. Or done all at once, you find the width of the interval by subtracting the endpoints, and then you divide it by 2, and there's your 30. So that's a whole lot easier than going in and using that formula. Just find the interval itself on the calculator, take those endpoints, which won't be as clean as 40 and 100, but I'm illustrating with easier numbers. Okay, let's go back to what we skipped over. I think we were on this screen. Here we go. Now we've got kind of some complex calculations here. How large a sample should we be taking? The sample size required for a particular confidence interval level is given by this formula. Now, most of us don't like this z of alpha over 2, so I've rearranged it here to inverse norm of alpha over 2. Now, let me just explain briefly where this formula comes from. If we were to go back to the previous screen, and I'm going to erase off this so I've got a little bit of space, and I took that formula that we have up here at the top, and I wanted to rearrange it and solve for n, the first thing I would do is I would divide off that z of alpha over 2, wouldn't I? So I'd say e over this z of alpha over 2 is equal to s over root n. Then to solve this equation for n, I would cross multiply. That would give me on one diagonal e root n equals s times this z of alpha over 2. Then I would divide off that e on both sides. That would give me the square root of n equals, and I'm going to write the z of alpha over 2 first, times s divided by the e. And then we would square both sides, which would give us n equals that stuff squared. Now, if you go to this screen here, n equals that stuff squared. So that's where that formula comes for those of you who have a little bit more of an algebra bent to you. Now, going back to our previous example with those IQs that you had in your calculator, we found this interval right here. Now, if I wanted to know what is the margin of error of this interval, just like we did on that interval a moment ago from 40 to 100, we're going to do the same exact thing. I'm just going to say, rather than using the formula, let's find half of the width of the confidence interval. So I subtracted those endpoints. I used parentheses, okay, to get that numerator. Then I divided it by 2. Now you need those parentheses there because otherwise you'll be going 113.93 minus half of the 105.67. Order of operations really requires those parentheses there. Now explain the meaning of the error E in this context. Okay. When we are 95% confidence in our interval, we are off by at most 4.13 IQ points. That's what the meaning of an error is, how much we are off by at most, the maximum error. Okay, so part C now says, and this is what you're going to be doing on your next test, in addition to finding point estimates, but find the sample size that we need so that we can be 95% confident that our estimate is within 2 IQ points. That 2 IQ points, whenever you see within 2 points, that's our margin of error. So let's take this formula and actually substitute in the key numbers. Now, before you actually substitute those in, you got to figure out this alpha over 2. So I'm going to start at the right here, and I'm going to say we begin with 95% confidence. That goes along with 5% significance. 5% significance, using the notation alpha for significance, that equals 0.05, and cut it in half, we get 0.025. This is something we do on every single sample size problem, and we just base it on how confident we want to be. Now we move on to actually substituting numbers into that formula. So there's my inverse norm. I substituted in this alpha over 2. I multiplied by sigma. Sometimes you don't have sigma and you have to use S instead. And then within 2 points, that was my margin of error 2. That becomes now a calculator exercise. Now, you've got to be familiar with your calculator, and I'm going to do the same exact step every time you see me do this. I begin on my innermost function. First, find the inverse norm first. And when I do that, here we go on our calculator, inverse norm, 0.025. It's under the standard normal curve, so I've got 0 and 1. And if you have the calculator where you have a choice of left versus right, you'll go left. But if you don't have the choice, you just leave that off. And that will give you this value. That's just the inverse norm. Then I'm going to multiply it by the 12 and divide by 2. So you can see I took my answer, times by 12, divide by 2. And that gave me what's inside the brackets. Then I need to square that. And when I square it, I get 131.29. And for these sample size problems, we always round up. Doesn't matter, there's a 0.2. We round up because we're trying to ensure that we are going to be 95% confident. If I round down, we won't be fully 95% confident. We only might be 94.9% confident. So we always round up on these problems. Now, part D says, okay, now let's find a 95% confidence interval for the mean. If the sample size that we just found in part C, that's what we just found here, yields a mean of 112. Okay, so we're changing some numbers around a little bit, but I'm going to begin by, why do I have that in? Oh, find the confidence interval. So that one, I wasn't doing a sample size. So now I said, let's go into our T interval. I've got the mean of 112 entered. I've got the sample standard deviation they told me to use, 12. I've got the sample size 139 that we just found that they wanted us to use. And I did 95% confidence. And here is my new interval. Okay. And then I just ask a question. Why was the mean value of 109.8 IQ points changed to 112? Okay, well, partly it's because I told you to go back and use the sample size of 139. Originally, it was just 30 pieces of data. And so it would seem reasonable that when more data is obtained, going from 30 samples to 139 samples, that the data is going to change. And that's why the mean changed for this sample. Whenever you go back and gather more data, things are going to change. Okay, we've done this quick little review. Let's do a couple more parts here. Okay, this one is just a practice problem here. I'm telling you the mean subscription rate for a law periodical was $29.66 back in 2013. That was back then. A random sample of 12 law periodicals yields the following annual subscription rates to the nearest dollar for this year. This year compared to back then. Determine a 95% confidence interval for this year's mean annual subscription rate. And I even told you what the mean and the standard deviation are. So you really have two choices. You can go into your T interval menu and choose data, okay, and then type in the list and use that list, or you can use stats and enter this mean and standard deviation. So please pause your video, do this, let's check yourself. And I'm going to tell you that when you do this, your mean, your interval, your 95% confidence interval should be from 41.385 to 52.115. Now, I'm asking you to use that to answer a question. Does this result suggest an increase in the mean annual subscription rate? Well, back in 2013, it was $29.66. And I'm going to say yes, our entire interval is far over $29.66. Okay, another example, a meteorologist who sampled 13 thunderstorms found that the average speed at which they traveled across the state was 15 miles per hour with this standard deviation of 1.7 miles per hour. Find a 99% confidence interval for the mean. Again, I want you to pause this and go and try this on your own. Now that you've unpaused it here, you could not enter your data into a list. You had to use the stats option. You had to enter the mean of 15, the sample standard deviation of 1.7, and your sample size of 13. And then you typed in the C level of 0.99, and the value that should have come out would be, or the interval, from 13.56 to 16.44. Now, the next question, I'm not going to test you on this, but it's kind of a question that's a little more practical. If the meteorologist wanted to use the highest speed to predict the time it would take the storms to travel across the state in order to issue warnings, what speed would they likely use? In other words, you want to be prepared. When's the earliest it can arrive? Well, we take the fastest rate of the storm because that will help us determine what would be the earliest time that it could actually hit a particular town. And that's why they're going to use the largest number, 16.44, or probably plan on 16.5, round it up a little bit so that you can be a little bit extra cautious. Okay, that brings us to the topic of now, how are we going to word confidence intervals? Okay, and we're going to use this phraseology. We can be blank % confident that, and then we write in the context of the problem is going to be between this and this units or percentages. Units right now, and it'll be percentages when we move on to the 1 proportion Z interval. And I've just got a reminder here of what this truly means, even though we're going to be using this language. And this true meaning we'll get at when we get into a problem towards the end of the chapter in the second video here. Now, I told you VVC is chosen to use t-tests, okay? And I've illustrated that we're going to use t when we're dealing with means and z when we're dealing with proportions. That was illustrated for you way back at the very beginning of this video when I said t goes with means, z goes with proportions, and we've crossed off some of these other options. Now I'm going to answer why have we crossed those off, okay? And I said in this box, recall when we use a t-curve, we must assume the data is approximately normally distributed. And sometimes if we're not sure, we try to create a normal probability plot or modified box plot to check the assumption. But even then, sometimes you can't do that. Now, it used to be, this is how I taught this if you had taken my class 20 years ago, it used to be, I said, okay, guys, you've got all these extra tests to choose from. And it used to be, if we go back 100 years, it was really only sample size. Small sample sizes, you go T, larger sample sizes, 30 and above, you go Z. But that was very simplistic. And then Texas Instruments came along and they said, okay, it depends on whether you have S or sigma. S, you go with T, sigma, you go with Z. And then that was a little bit too simplified. And we do know that normality is actually required here. And we don't know, we prefer normality, but it's not actually required for a Z. So what I used to do, and this is not what you're doing, but just so you have a reference, is I'd say, okay, I want you to look at these 3 criterion, and if you can get 2 out of 3 going in one category as opposed to the next, that's how you know when to use Z versus T. We've got it a whole bunch easier here because this is the way we're going to go. And it's consistent with other schools because in real life, seldom do you have the population standard deviation. You're almost always using samples. And for that reason, the T-curve is the way to go instead. And it really doesn't matter once you start getting to larger sample sizes. Okay, let's do a final example here and then we'll cut it off and we'll switch to a second video here. I think this is my last one here. Yep, it is. Okay, Joe and Sally are going to construct confidence intervals from the same simple random sample. Joe will construct a 90% confidence interval and Sally will construct a 95% confidence interval. Which confidence interval will have the larger margin of error? Now, there's a couple ways you could do this. If you were to draw a picture, let me find my cursor here. Here is a picture here, and I'm going to say, here's one confidence interval, and I'm going to make it 90%. This is being exaggerated, but here's 90% right there between these 2 markers. Then I have another one where I say this is 95, like that, 95%, a little bit wider. Which one has the larger margin of error? Well, that's looking at this E from the center to the edge And you can see that center to edge, this value of E is going to be larger on the 95% interval. And so there you go. Sally's interval, which was the 95%, will have the larger margin of error. Which one is more likely to cover the population mean, which will have it within that interval? Well, again, the 95% one is wider, and so that's the answer there. I like to think of it as a goalie in front of a hockey goal, and the more padding you have on, the wider you have a better chance of blocking and covering that interval. Whereas if you have a little skinny person without the padding trying to block a goal, you're not going to necessarily be able to catch the puck as it comes through. Now, I just explained how to answer this question conceptually. If for some reason your brain doesn't work conceptually, you can take any old data set. It doesn't matter which one you happen to have in your calculator. And I don't even know what data set I have here. And basically, you can say, let's do a T interval based on that same list. The first time I did it with 90% confidence. Second time I did it with 95% confidence. And here are the two corresponding T intervals. Now, what I did is I basically subtracted the endpoints to see how wide they were. And you can see here that the second one that goes with the 95% confidence interval is wider. So if you don't have the concept down by using these pictures down below, you can just make up a data set and test that data set to determine which one has a wider interval and which one also will have a larger margin of error. Now, when we come back, we're going to start moving on to the proportions and really dive a little bit deeper into what does this phrase, we can be 90% confident, actually mean.